Hello and welcome. I'm Peter DeGroot. I'm speaking to you from Zygo Corporate Headquarters in Connecticut. My co-authors and I would like to thank you for tuning into this presentation. Over the next few slides, I hope to convince you that a Fourier Optics model, even a simple one, what we call an elementary Fourier Optics model, can provide important insights into the behavior of interferometers that measure surface form and texture. All right, let's go. We'll begin with motivation and goals. Why are we working on this? What does this do for us? Then I'd like to introduce this elementary Fourier Optics or EFO model. That's what we call it. It's a basic model of an interferometer that includes the optical imaging properties of the instrument. Then we'll take a look at what the limitations are of such a model. You know, if it's very simple, what have you given up? What are the boundaries of usefulness for such a model? And I'll provide a practical example, the lateral resolving power, how close together can features be, how high could the spatial frequency be on your part, and still be able to get useful information out of your interferometer. And then finally, I'll introduce an EFO demonstrator using Excel that you can download, play around with, and maybe be inspired to improve and write your own program for modeling interferometers. All right then, let's get started. So, motivation, why bother doing this? Certainly one of the reasons for spending time on modeling is to answer a very important question for those of us that make and sell interferometers. Does it work? So this was from last year's presentation at San Diego. Does interferometry work? And of course it does, but it has some interesting features and sometimes surprising features. I'll give you just one example. Many people are surprised that as you change the spatial frequency content of the surfaces, the response of the instrument changes. As a matter of fact, the higher the spatial frequency, the less the interferometer responds. This is, again, well understood, and it's understood from modeling, and we know why this happens. So it's not necessarily a bad thing, but it is something that we need to be aware of, and modeling certainly helps in understanding what the instrument response is. Another reason, of course, is to get the best possible results. You want to optimize the measurement. So a good model will tell you under what conditions you can get the best possible results for a certain type of part and environment. A good reason to have an interferometer model is to be able to predict if metrology goals can be achieved before you even try and make a measurement. For example, we expect that little lenses like this, we should be able to measure those no problem. Even if there's some steep slopes here, there is a solution. For something a little smaller, like this thin film transistor on a display, that's only 40 microns wide for the field of view, but you can measure that in an interference microscope. That's not that difficult. What about this transistor on a silicon wafer? This is a little bit of older transistor, but still pretty small. You see the 100 nanometer scale there. You might be able to measure that. The features are not that close together. A model could tell you whether or not you're within range or what kind of numerical aperture or wavelength you would need. But then if you want to try and measure a part for the individual atoms, for example, in silicon that you can see here in an atomic force microscopy image, that's on the nanometer lateral scale, and it's very unlikely that you're going to be able to see anything like that. And that would be predicted by a model. You wouldn't have to do the experiment to know. You also would like to do modeling to design and build better instruments. So we do a lot of this. Shiguan Wang and Les Deck at Zygo have developed a number of ways to characterize instruments and predict their behavior, optimize the optical design based on instrument transfer function, other tools that characterize response. So modeling the interferometer using Fourier optics and other techniques is certainly important for that, and it's a big part of what we do. Another thing you could do with a good interferometer model is to evaluate uncertainty. Suppose you've identified a series of sources of error, focus aberrations, vibrations, steep slopes, and so forth. You could certainly do some experiments to find out how those things are influencing the uncertainty of your final result. But it would sure be nice if you could just do that numerically in a computer in what's called a virtual instrument, and then you get an uncertainty at the other side. And there are a variety of different approaches that you could apply to this, including machine learning. So clearly there are a lot of good reasons to model interferometers. But the next question is, what kind of interferometer model do we need? What's the best model? Perhaps the best model is the one that's the most rigorous. And those of us that are trained in physics, we immediately gravitate towards this as the best model because it has lots of fun problems to solve. You could use rigorous coupled wave analysis, boundary element analysis, a number of different techniques, and you can write all kinds of MATLAB code, and it's great fun. And there are times when you have to do this in order to get a meaningful answer. So maybe this is the best model. Maybe it's the model that has the most 3D aspect. After all, it is a 3D problem. We're looking at surface structures and topography, so that's an XYZ structure. We should probably come up with a model that is 3D inherently. And this has been done a lot in microscopy. A lot of microscope imaging is volumetric, and so getting the three-dimensional point spread function and the corresponding three-dimensional optical transfer function is very important in microscopy. In recent years, these types of ideas have been extended to interferometry, including by our collaborators at the University of Nottingham, at Loughborough in the UK, and elsewhere. 3D transfer functions are increasingly common. Maybe the model that we would like to work on is the one that solves the hardest problems. I mentioned semiconductors before. So there's a semiconductor wafer. Maybe we want to look at those things that are printed on a semiconductor wafer, certainly high value. So here's work that was done some years ago now using interferometric scatterometry beyond the diffraction limit. So looking in the pupil plane of the interferometer and using rigorous coupled wave analysis and getting all kinds of information about the object, including film thicknesses and the edge roll off and so forth. So maybe that's what we should be doing for our model. There are lots of different things you could do. I mean, all these advanced models are essential. As you increase the range of applications, different surface structures may demand different models to get decent results. However, just for today, I'm opting for the easy path. What I'm looking for is the simplest possible interferometer model that includes the imaging properties of the optical system, and I mean in a realistic way. Not in a trivial way. So something that tells me how is the fact that I'm looking through lenses and limiting apertures, how is that going to affect the behavior of my interferometer, and what can I learn from that that doesn't require too much time to code? So that brings us, what are the goals of a simple model? The goals for a simple model are quite modest. We're looking for a first model for students and researchers, something to get started. We'd also like to gain some insight into the more fundamental sources of error, the things that we see all the time, so that we can avoid these error sources in designing our experiment. We'd like to be able to do fast calculations of uncertainty with a model that is not so computationally intensive, so that we can do lots and lots of calculations fairly quickly, for example, for this virtual instrument. And then finally, if you've done your job of rigorously solving Maxwell's equations, it's always good to compare the results to a very simple model to see where such an advanced model provides added value. That's a good thing to do. To meet the goals of a simple model, we developed this elementary Fourier Optics method for interferometers. The first thing that we're going to do is we're going to look at this 3D surface and we're going to see if we can simplify that thing, because it's kind of hard to work in 3D. Topography is 3D. So in Cartesian coordinates, you have x, y, z. So clearly you have to express every point in the topography by an x, y, and a z. We usually do that by a 2.5D representation where you have surface heights as a function of x and y. But the next step that we find very natural, but actually is quite dramatic, is we're going to take those surface heights and we're going to translate them into phase values for a complex valued transverse object. So all of the surface heights will now just become phases. And the phase shift you can calculate from the surface height and the equivalent wavelength. And what you now have is an object that has only a 2D structure. It's just within that 2D structure, you have these phase values. The next step is to choose your diffraction model. So we're going to choose simple scalar diffraction. It's the easiest thing to do. And for that, you end up with a spectrum of plane waves after the light reflects from the surface. And plane waves are the free space solution to the Helmholtz equation. That's why we're using them. The spectrum of plane waves is the Fourier transform of the complex reflected field. And in the far field of this scattering pattern, you see something that actually corresponds to this Fourier transform of the complex reflected light field. And of course, in an optical system, we usually use lenses and mirrors and so forth to create the far field without going off to infinity. But that's the basic idea. The next step is where our Fourier optics comes in. We're going to take our part, we're going to shine light on it, and that will give us a complex reflected field. And then we're going to feed that into an optical system. And that optical system is going to apply some optical filtering that might attenuate or even distort the signal somewhat. Once that's done, we're going to look at the complex imaged light field that comes out the other side. And to get the surface topography, we have to interpret the phase values of that complex image light field, and that gives us the measured topography. So a lot of that's what's important in this model is how the optical filtering takes place. And that is typically in a Fourier optics model characterized by a transfer function. The kind of transfer function that we use to characterize the optical filtering properties of the instrument depends strongly on the light source and the illumination geometry. If you've got a laser piezointerferometer or laser-based interferometer, then the light is fully coherent and the filtering is linear in the complex amplitude. So we use the amplitude transfer function. If, on the other hand, the light source is incoherent, the light's coming from pretty much everywhere, like in the situation where you've got a picture camera and you got ambient light from all around, or maybe it's a room lamp, something like that. That incoherent light source means that the filtering will be linear in intensity as opposed to complex amplitude. And for that, we use the optical transfer function. So the optical transfer function is for incoherent imaging, and then the amplitude transfer function is for coherent imaging. It's a little more complicated for microscopy. For the kinds of microscopes that we usually encounter in interference microscopy, you have epi-illumination. You have an extended source which shines down on the object, and then it's reflected often back through the same limiting aperture of the objective. In this case, the illumination and the optical properties of the system are neither fully incoherent or fully coherent. It's somewhere in between. The light is partially coherent, and consequently, it's not linear in either intensity or in complex amplitude. Now, often you can still use the optical transfer function under the special condition that the illumination numerical aperture or the condenser numerical aperture is equal or greater than the imaging numerical aperture. But that has a lot of limitations. That's only true if the object is perfectly diffusing or perfectly flat. In other words, you can't have any surface topography, or the part can't be polished. So that's not so interesting for us. So we looked at this situation recently in the context of interferometry, and we're able to show that you can do some things here with a 2D surface model, as we've described. And if you make some actually fairly common approximations, like the use of an obliquity factor to account for all of the incident angles of the illumination, you can linearize the optical filtering for the interference fringes, not for the conventional imaging, intensity imaging, but for the interference fringes, you can actually model a system as if it were fully coherent, but it had a transfer function that looked very much like the optical transfer function. The model uses a partially coherent transfer function, or PCTF. So what is that thing? It is a linear shift invariant frequency domain function, and it includes the limiting apertures, but also defocus, optical aberrations, and so forth. If you've got a diffraction limited system, then it's the cross correlation of the illumination pupil and the imaging pupil. This is a calculation that's familiar in conventional microscopy for what's called, in that context, the apparent transfer function. And the result looks something like this. As a function of spatial frequency, you see that things start to taper off as the cross correlation starts to tend towards zero for the higher spatial frequencies. It's quite important to realize that phase objects, that is, like topography objects that create this phase shift, are not like images. The plane wave spectrum strongly depends on the surface height. So here's an example where you have a sinusoid. It's the same period sinusoid in both of these graphs on the left and the right. The difference is the amplitude of the sinusoidal topography feature. And you can see for a larger amplitude, you get many more diffraction orders. And all of these diffraction orders have to be captured by that partially coherent transfer function to get good linear results. So this is something that's very important to know. So even though the transfer function for the light field is linear for a wide variety of circumstances, the interferometer response may be nonlinear. And that's one of the reasons why you want to do modeling, is to find out when it might be nonlinear. All right, when can I use an EFO model? There are quite a few limitations of simple methods, and I'm going to answer this question by giving some examples of where an EFO model is unlikely to be successful. Here's an example right away. This is the somewhat tortured surface of an additively manufactured part. This is actually measured with an interferometer. You can do this now. It's a very good way to measure additively manufactured surfaces, but we do not expect a simple Fourier Optics model to be able to predict the results or to provide you with an uncertainty of this measurement. So that's just too rough. Another example is a surface that has a lot of sharp edges in it, particularly if these are over a quarter wavelength. You can get edge effects, you can get multiple scattering effects that are beyond what the EFO model can handle. And then another example, which is straightforward, is if the light is not making it back into the objective because the surface slope is too high. You might actually be able to measure a part like this. It's also very common in interferometry to measure parts that are outside of the slope acceptance of the objective, but you're looking at the scattered light off of the surface, and the EFO model is not designed to manage that. And finally, of course, the part should be relatively flat. So that's the question. Just how flat does the surface have to be for this EFO model to work? The answer to that question depends a lot on the specific kind of data acquisition. Interferometers measure surface topography in different ways. One of the key differences is whether or not the focus position is fixed. For example, in phase shifting interferometry, you measure the interference phase by going through a sequence of phase shifts over one cycle. It's usually a monochromatic light source or near monochromatic, and the focus position is set. On the other hand, coherent scanning interferometry, very popular in interference microscopy, the focus is scanned with the optical path length. So the reason for doing this is we're going to use both fringe visibility and phase, and you often are using white light. So two very different ways of acquiring the data. In this presentation, we're going to concentrate just on those types of data acquisition that involve a fixed focus position. So phase shifting interferometry, PSI microscopy, laser Fizeau interferometers, those types of interferometers that do not scan the focus position during the data acquisition. So how flat does the part have to be in order for the EFO model to work for a fixed focus system like a phase shifting interferometer? Well, the model is a 2D approximation to a 3D problem. So to get a good idea about what the limits are, we can use a full 3D model, a 3D transfer function model that treats the object actually as a real surface topography rather than this flat aperture function. To do that, we rely on a 3D TF model. We're calling it a 3D TF model. It's also called the foil model, that was created by Jeremy Coupland and colleagues, and has been further developed by Professor Richard Leach and Dr. Rong Su at Nottingham. And this is a very good way of evaluating more realistically what is going on in the interferometer, particularly if you're trying to find out what the limits are of a 2D approximation. As a first comparison example, we'll take a relatively small numerical aperture, 0.1, and we'll look at a sinusoid. You see the object surface profile there with a 20 micron period. If we apply the EFO model, we get these types of predicted results. There's the measured profile, and there is some predicted measurement error having to do with not quite capturing all of the diffraction orders, all of the spectrum of plane waves. If we overlay the results from the more realistic 3D TF model, we see pretty good agreement. So that's a good result. So that says that under these conditions, with this type of an object profile and this numerical aperture, we can use an EFO model. The results look still good at a higher NA, as long as the surface heights are pretty small. So here we have a numerical aperture of 0.3, and we've got two posts, and they're short posts. They're 40 nanometers tall. And what we see with the EFO modeling is that these posts will not be perfectly rendered in a measured topography that you would expect. They're a little bit blurred. And if you overlay the results from the three-dimensional model, the more realistic model, you see, again, very, very good agreement. So that's great. So at a larger NA, as long as the surface heights are small, we're in good shape. You can continue this exercise by saying, okay, well, what if we take those two posts and the numerical aperture of 0.3 and we intentionally defocus the system by 5 microns. So we're gonna take the part and we're gonna move it out of focus by 5 microns. Well, the focus blur gets to be greater. That's expected. And if we overlay the 3D TF, we see that both models show about the same amount of defocus blurring, although the 3D TF shows a somewhat different high spatial frequency detail. But the agreement is generally pretty good. So I would say that you can quantify defocus in an EFO model. Let's try something a little bit more challenging. Here we have a part with a lot of surface departure, plus or minus 4 microns, which compared to the depth of field is pretty large. And we're going to expect to see some difficulties here because the model, the EFO model, is blind to focus errors within the field of view. The previous example, we were putting the object at different focus positions overall, defocusing the instrument. But this is a case where the departure itself is introducing defocus. If you go ahead and run the EFO model, you see pretty good results. Measurement error is close to 0, except at the very edges where the light is actually falling outside the acceptance cone of the numerical aperture. But if you run the 3D model, the 3D transfer function model, you see variations on the order of 10 nanometers almost. These are caused by focus effects, and we expect that in this case, the 3D TF approach is going to be more realistic than the EFO. When we think about the focus effects over the field of view, a natural parameter for that is the depth of field. And we can see here in this list of objectives how the depth of field gets smaller and smaller as we go to higher and higher numerical apertures fairly quickly. It's a quadratic relationship. So this tells us that if you've got a lot of surface topography, you're probably going to be limited to low numerical aperture if it's a non-scanning system like a phase shifting interferometer. Now that we got this approach in our toolbox, let's take a look at some results related to lateral resolution. For imaging systems, the modulation transfer functions tells us how well the system can respond to closely spaced features, particularly these sinusoidal patterns. As the sinusoidal pattern gets to be higher and higher frequency, then generally the response of the instrument will decline. And that's characterized for incoherent imaging by the optical transfer function. The analog of the imaging modulation transfer function for surface topography is the instrument transfer function. So if the system is linear, you can use this instrument transfer function. That tells you how the interferometer, the measuring instrument, will respond to topography variations. Now what we found is with the EFO, if you have small surface height variations, then the ITF is approximately equal to the optical imaging MTF. So this was shown some years ago, and it's a nice result because it means that if you calculate the theoretical MTF, you have a fair idea of what the transfer function characteristics are going to be of your interferometer. So this compares here the measured ITF, what is actually measured on the instrument as the response characteristics compared to this theoretical MTF, and you can see they follow each other quite closely, again, for small surface heights. For larger surface height variations, larger than this lambda over 8 limit, we find that the response of the instrument varies a little bit. It's no longer following the MTF perfectly. So for example, if we say, let's go through a series of sinusoids that meet a slope limit, in other words, the maximum slope on the part is not so large that the light is deflected outside the acceptance in A of the objective, then you could have a peak value of up to 2 microns, which is much bigger than the small height limit at 10 nanometers, inverse nanometers, and 0.2 microns at 100 inverse nanometers. And if you calculate using the EFO what the response of the instrument is, Curiously enough, you find that it's a bit flatter, out to 0.1 inverse microns spatial frequency. So that's a kind of interesting result. I think the key takeaway is that you can calculate this with this model, and that's a useful thing to do, and the calculation is quite quick. So we did an experiment to verify this. We found a sinusoidal sample at close to 0.1 inverse microns, at 0.125 inverse microns, and we did the measurement. And what we found was that indeed the experiment matches the theory very well, and that the attenuation at this spatial frequency is about 13%, not the 25 or 26% that we would have expected if we were following the MTF. So that gives us some confidence that we are accurately predicting the response of the instrument. One of the more frequently asked questions is, what's the lateral resolution limit on my interference microscope, for example? So let's put in a 100x objective with a 0.85 NA. So this is really challenging the limits of scalar diffraction theory if we want to make a prediction with the EFO model. The other limit, of course, is that it must be a fairly flat object given the depth of field at that NA. So we can find that. Here's a very flat object, a supercon silicon on quartz sample with two trenches that are 26 nanometers deep, a center line that's only 200 nanometers wide. So would we expect to be able to see this in our interference microscope? Well, running the EFO model for a 570 nanometer wavelength, the prediction is that yes, you will be able to see that there are two trenches. It's blurred, that's to be expected. They're square profile trenches, and we're seeing them is not quite as distinct as they actually are. And also the depth is measured as 9 nanometers, not 26. Let's test this prediction in a real instrument. We'll use a Zygo NuView 3D optical profiler, and indeed we get a profile that looks very similar to what the EFO model has predicted. The one difference is that we only are seeing a 3 nanometer depth. So this is almost an 85% reduction in the actual versus the measured depth. But it's not too surprising that there's a difference. We've neglected all of the dissimilar material effects. We're using scalar diffraction theory and so forth. But the model does predict, the simple EFO model does predict that you should be able to separate those two lines. So that's good to know. Whether you're an instrument designer or a user trying to optimize a new application, there's a lot of value in having an interferometer model to give you some idea of what the response of the instrument will be under certain circumstances. Consequently, some of our research recently has been concentrated on identifying models that are more readily accessible to a wider audience. One of these is this EFO model. This uses traditional Fourier optics to characterize the imaging properties of the system and to give you an idea of things like lateral resolution, the potential for nonlinearities if the numerical apertures are not high enough, and so forth. The model's simple enough that you can implement in any one of a number of different programming languages, pick your favorite. We thought it'd be kind of fun to do it in Excel. So we implemented in Excel a version of the EFO, very simple implementation where you can change the surface profile characteristics. There's a sinusoid, and you can see the difference, the approach of nonlinearities, the spectrum of plane waves, the transfer function when you exceed the slope limits. You can change the optical system. You can change the numerical aperture. You can change the object to twin posts, and you can see what happens if you change the focusing properties, go from 0 to 4 microns, even 8 microns defocus and back. You see how things might be blurring. You can challenge the limits. It's identified by the Rayleigh criterion. So it's quite a fun thing to work with, again, as a starting point. To close the presentation, I'd like to acknowledge Project Fidelity. This is a collaboration between industry and academia with the goal of improving the performance of interferometers for all kinds of applications, including the latest applications with the most difficult type of manufacturing technologies. With that, I'd like to thank you for your attention. I look forward to your comments. I also look forward to hearing about your experiences in interferometer modeling and your ideas about the next steps.